Hi there. Welcome back. This is lecture 6 of machine learning from data, and today we're going to be talking about bounding the growth function. Okay, and just to remind you, the growth function is this new measure of complexity that we introduced for a hypothesis set, which views the complexity of a hypothesis set through the lens of a data set. Okay, and the advantage here is that it reduces infinite hypothesis sets to finite collections of dichotomies. And now we're going to analyze those finite collection of dichotomies that can come out from hypothesis sets that we'd like to use in practice. Okay, now before we get going, let's have a recap of what got us here. Okay. So, we introduced the growth function, which is this way of looking at a hypothesis set through the lens of a data set. And on the top right here, here's an example hypothesis set, and here's a data set. And when you view through this data set, this hypothesis set, which has many hypotheses, is very simple. It just has effectively the ability to implement one function on the data set and on that data set. And a function on that data set is basically what we defined as a dichotomy. It's a way to assign, plus and minus to the data, to the points on this in this data set. So we introduced this notion of the growth function, which says, pick any data set you like, x1, x2 up to xn, and compute all the dichotomies that your hypothesis set can implement on those data points. Okay, and that's a measure of the complexity of the hypothesis set, the diversity of dichotomies it can implement on this particular data set. Now maximize that over all possible data sets of size n. So, go and find the worst possible points x1 to xn that you can in order to try to increase the complexity as much as possible. And then this maximum possible complexity, this maximum number of dichotomies, that can be implemented by the hypothesis set is sort of an upper bound on the complexity of the hypothesis set as seen through any data set. Okay, and this is what we call the growth function. It's the maximum number of dichotomies that a hypothesis set can implement on n points. Okay. And in this lecture, and last time we sort of asked, this growth function is at most 2 to the n, and then we showed that, in infinite hypothesis set examples that, it's significantly less than 2 to the n. So the question today we're going to answer is, and we will answer this, definitively, rigorously with a proof, can we bound the complexity of a hypothesis set? Okay, not by the trivial bound of 2 to the n, but by a more useful bound that's polynomial in n. Okay, so we will answer that question. And then the next question that, we posed last time was, is this effective complexity of a hypothesis set, this growth function, is it useful? Does it provide us with an error bar that we got in the finite hypothesis case? Now, we won't go through the detailed proof there, but, you can look in the text, and indeed, a similar probabilistic argument using a version of the Hufting and also a union bound will allow us to replace the size of a hypothesis set with, some version of this m sub h, this growth function. Okay, so just a recap of the 3 hypothesis sets that we considered last time as examples of growth functions. So we considered the 2-dimensional perceptron. Okay, and we saw that with 4 data points, the two-dimensional perceptron cannot implement all 16 dichotomies. Even though in theory, if it was, it's got uncountably many hypotheses and it should be able to do anything you want on just a mere 4 data points, but it cannot implement all 16 dichotomies. So this means that the 2D perceptron is broken. Okay, a deficiency of this hypothesis set has appeared, and it has appeared at just 4 data points. You cannot implement 16 dichotomies on 4 data points. Wow. We thought this is an uncountably large hypothesis set, but it's infantile. It gets destroyed by 4 data points. Okay. The one-dimensional positive ray also uncountably infinite, but that gets broken at 2 data points. You cannot implement all 4 dichotomies on 2 data points. Okay. And the 2D positive rectangles that we considered last time, that's a little more powerful. Okay, it only gets broken at 5 data points. Now, we didn't compute what the growth function is. We just proved that it's broken. Okay, and this shows at least that there's hope. Okay, that some reasonable, infinite, uncountably infinite hypothesis sets do get broken. So this trivial bound of 2 to the n, these hypothesis sets that we consider can't achieve that. Cannot classify a typical data set of size n if n is large enough, cannot classify that data set in all possible 2 to the n ways. So there is hope. Okay? There is hope that these hypothesis sets, when viewed through data sets, are not exponentially complex. They may be polynomially complex. Okay? And what will play a key role in the analysis that we're about to discuss is, when does the hypothesis set get broken? Okay. And what we see here is that in all cases, these 3 hypothesis sets do eventually get broken. So let us define a breakpoint. Okay. So a breakpoint is a value of n that reveals the deficiency of a hypothesis set. Okay. What that means is that for that number of data points, and we'll call the breakpoint k, it's a value for the number of data points k that reveals the deficiency of a hypothesis set. So what that means is that, if you have k data points, there is some dichotomy that cannot be implemented on those data points. So what that means is that, and that's true for any data set of size k. So what that means is that the maximum over all possible data sets of size k is strictly less than 2 to the k. So what that means is that the growth function is strictly less than 2 to the k. And any number of data points for which this holds, we will call it a breakpoint because it's broken the hypothesis set. Okay? It's revealed its deficiency. Okay. And, the goal today is to analyze this beast called the growth function. We're going to come up with a very, very beautiful result. Okay, and in order to analyze this growth function, we're going to gain considerable traction by going back to that combinatorial puzzle we discussed last time, and analyzing that puzzle fairly carefully. So it might look completely unrelated. Man, why? I didn't take a class in combinatorics. Why am I having to analyze a combinatorial puzzle? Well, turns out that it has a very, very deep connection to this growth function guy. Okay. Before we tackle this combinatorial puzzle, let's get some practice with breakpoints and growth functions and dichotomies and all that stuff, because we've thrown a lot of stuff at you, and it's good to get some practice. Okay. So pop quiz 1, I give you a set of k-star points, okay, a specific set of k-star points on which h implements fewer than 2 to the k-star dichotomies. So we introduced a term for that. We say that h does not shatter your k-star point. So what do you know? A, k-star is a breakpoint. B, k-star is not a breakpoint. C, all breakpoints are greater than k-star. D, all breakpoints are less equal to k-star. E, we don't know anything about breakpoints. Okay, so pause the video. Okay, and if you pause the video and are back, or you just continued and are here for the ride, and if you said E, we don't know anything about breakpoints, then you have a good understanding of what it is to be a breakpoint. Okay, so, to be a breakpoint, you must show that, your hypothesis set cannot shatter any data set of size k star. Okay. One data set of size k star is not sufficient. You have to demonstrate that your hypothesis set is deficient no matter what the set of points. Okay. And that's just the definition of a breakpoint. That's the definition of the growth function. Okay, pop quiz 2. Now, for every set of k star points, you can show that h implements fewer than 2 to the k star dichotomy. So h fails to shatter any set of k star points. Okay. What do you know? A, k star is a breakpoint. B, k star is not a breakpoint. C, all k greater or equal to k star are breakpoints. D, all k less than k star are breakpoints. Okay. And E, we don't know anything about breakpoints. Again, pause the video, and okay, if you answered, A, k star is a breakpoint, you know what a breakpoint is. Okay, so that's the definition of a breakpoint. A breakpoint is a value for the number of data points, in this case k star, such that you have revealed a deficiency in your hypothesis set no matter what set of points you choose. So for every set of k points, it is the case that h cannot shatter that set of k points. Okay. Now, if you observed that once you have found a breakpoint, if your hypothesis set cannot shatter k star data points, no matter how you arrange them, then you cannot shatter any larger value, any larger number of data points, no matter how you arrange them. Then you would have said C, and that's that's great. You have an even deeper understanding of breakpoints. And if you said A and C, then you got it perfect. Okay, because both A and C are correct. Okay, you know that k star is a breakpoint. You also know that everything larger than k star is a breakpoint. Okay, pop quiz number 3. to show that K is not a breakpoint for H, for your hypothesis set H. What do you have to do? So now we're asking you, how will you show that you don't have a breakpoint? Okay, so show some set of K points which H can shatter. Okay, show that H can shatter any set of K points. Okay, show a set of K points which H cannot shatter. Okay, show that H cannot shatter any set of K points. And lastly, show that the growth function m of K is 2 to the K. So to show that K is not a breakpoint. Okay, again, pause the video. Okay, and if you're coming back, okay, and you said A or E, perfect. Okay. So what does it mean for K to not be a breakpoint? By the definition of a breakpoint, it means that you're a breakpoint if you cannot shatter any set of K points. You're not a breakpoint if you can shatter some set of K points. Okay, so that's A. And that's equivalent. If you can shatter some set of K points, then you can implement 2 to the K dichotomies on that set of K points. And since the growth function is the maximum number of dichotomies you can implement on K points, the growth function is 2 to the K, and that's equivalent to the statement you can shatter some set of K points. Okay, so A and E are essentially equivalent from the way we define the growth function. Okay, now if you said B, okay, technically you're not wrong, it's just that it's overkill. You don't need to show such a strong statement that you can shatter any set of K points. So that's not required for K to not be a breakpoint. All that's required is that you have to be able to shatter at least one set of K points. Okay, now C and D, show that, a set of K points cannot be shattered. Okay, and show that, any set of K points cannot be shattered. Those are not moving towards showing that K is not a breakpoint. Those are moving towards showing that K is a breakpoint. Okay, so to show that it's not a breakpoint, you must show that you haven't revealed any deficiency in H, which means that H can implement all 2 to the K dichotomies somewhere. Okay, and last pop quiz number 4. Okay, now we want to show that K is a breakpoint. So it is a breakpoint. Okay, do we show a set of K points which H can shatter? Do we show that H can shatter any set of K points? Okay. Do we show a set of K points which H cannot shatter? Okay. Do we show that H cannot shatter any set of K points? Okay. Do we show that the growth function m of K is greater than 2 to the K? Okay, so now pause, answer, and if you're coming back, and if you said D, fantastic, you know how to show that K is a breakpoint. Okay, now let's take these. A and B are showing that H can shatter. Okay, and those are moving not towards showing that it is a breakpoint, revealing the deficiency of H. They're moving towards showing that H is, able to conquer K points. In A you show that H can conquer some set of K points. In B you show that H can conquer any set of K points. Okay, a breakpoint is revealing a deficiency. You've defeated H. You've broken H. Okay. Now, a breakpoint is only a breakpoint if H cannot conquer any set of K points. If you show one set of K points, like we did with the perceptron and putting the points on a line, that's not sufficient to show that you've broken H, because you've just chosen a very peculiar set of K points. You have to show that you cannot shatter any set of K points for K to be a breakpoint. Okay. And if you even thought for a minute about E, then you really need to go and review last lecture, because, by definition, the growth function cannot be bigger than 2 to the K. Okay. It's upper bounded by 2 to the K. Okay. So E is just, it's not possible in any world where we define the growth function as a number of dichotomies on K points. Okay, let's get now back to the combinatorial puzzle, and let me first remind you, what was that combinatorial puzzle? Okay, so I give you 4 points, x1, x2, x3, x4, and I've shown here, 5 dichotomies on these 4 points, where the plane circle is a -1 and a filled-in circle is a +1. Okay, and the key fact about these dichotomies that we have listed is that if you zoom in on any pair of points, you will find that only 3 of the 4 dichotomies on that pair of points are listed. So let's, for example, focus in on, let's say x1, x2. So x1, x2. Let's focus in on x1, x2. and look at the dichotomies that we have. We have minus, 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 minus. So minus, minus is repeated 3 times. And then we have minus, plus, plus, minus. So the only 3 dichotomies that are listed on those 2 points are minus, 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 plus, plus, minus. Where's plus, plus? It's not there. Okay. And if you focus in on any pair of points, you will see a similar phenomenon that we haven't managed to implement all 4 dichotomies on any pair of points. And that's a constraint. And then the question was, what's the maximum number of dichotomies that you can add? Okay, now if you worked on this overnight or you thought about this from last lecture, and you realize that you cannot do more than 6, then you are correct. So 6 is the maximum. It's the maximum number of dichotomies that you can list on 4 points such that no pair of points is shattered by those dichotomies. Okay, and let's just see an example of what happens if we try to add another dichotomy. So now look what I've done. I've added minus, plus, plus, minus. And you can play around with this and add any dichotomy you want. Okay. And now let's look at the pair x2, x3. Okay, I've highlighted the pair here. And if we look, we see we've got minus, 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 minus. Okay, we've repeated minus, minus. Okay, now we've got minus, plus, plus, minus. Now we've got minus, minus, plus, plus. So we've got minus, 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 plus, plus, minus, plus, plus. So we have all 4 dichotomies, and we say that that pair of points is shattered. Okay, because all 4 dichotomies on those 2 points have appeared. Okay, so now what we're going to do, we're going to move to the board, and we're going to analyze this in a much more general setting where you can have endpoints, and we are not going to just restrict ourselves to focusing in on 2 points. We have endpoints, and we would like to zoom in on k points and require that no subset of k points is shattered.